So in this video we're going to go over the concept of analyzing antiderivatives but through graphs. In particular we're going to be given the graph of the derivative and we're going to try to get information about values or particular values of the antiderivative. Alright, so I've set up this problem here where we have the graph of the derivative f prime in green here. And the question or the problem is going to be to put the following values of the antiderivative in increasing order, for example. All right, so f of 0, f of 2, f of 6, f of 8. We're going to have to figure out what those values are. And the little extra thing that we're going to have to use is that we actually know what one of those values are. We know that f of 2 is equal to 6. Remember, that's the value of the antiderivative. So I'll just put it right here. We already know that that's 6. So we just have to find the others, f of 0, f of 6, f of 8, and then we'll order them from smallest to biggest. So how are we going to do that? We are going to look, first of all, or we're going to use, first of all, the fundamental theorem of calculus, which says that the total change in the antiderivative is equal to the integral from a to b of the derivative, okay, of f prime of x dx. And this is again fundamental theorem of calculus. I'll just put FTC for short. And how are we going to use that formula to get these values? Well, it's simple. B, for example, can be 2, A can be 0, and then you can solve for f of 0, right? Because we know what f of 2 is. So let me just say that now in math. So we know that f of 2 minus f of 0 by the fundamental theorem of calculus is equal to the integral from 0 to 2 of f prime of x dx. Well, f of 2 we know is just 6. F of 0 is the thing we want to know. So we want to solve for that. Let's put it on the other side, and then we'll put the integral on the left side. And so what does that give us? That gives us that f of 2 minus the integral from 0 to 2 of f prime of x dx. That's going to equal f of 0. And there you go. That's what f of 0 is equal to. The only thing we're going to have to know is this integral. Okay? So let's go ahead and do that. Let's put this off to the side. Okay? Let's erase this part. Well, not now. Let's keep it there. And how are we going to find that integral? Integral from 0 to 2 of f prime of x dx. Well, that's where the graph comes into play. That means we're going to want to find this area right here. It's just the area of a triangle, so that's going to be no problem. Base is 2, height is 2, so 1/2 times 2 times 2 is going to be 2. Okay, great. So this integral, again, is going to be 2. So finally, f of 0 is going to be equal to 6 minus 2, which is 4. All right, so that's one value, and we're going to compute the other values in the same manner. So let's give ourselves some room here. Move that down. Let's do the same exact thing with or for f of 6. Okay? We know that by the fundamental theorem of calculus, f of 6 minus f of 2 is equal to the integral from 2 to 6 of f prime of x dx. Since I want to find f of 6 and I know f of 2, I'm just going to do the same thing. F of 2 on that side, integral on the left side. This is going to give us f of 6 equal to f of 2 plus the integral. Oh, sorry. Let's not put the integral on the other side. That's not necessary. Let's just keep it where it is. Okay? That's equal to, so f of 6 is equal to f of 2 plus the integral from 2 to 6 of f prime of x dx. We know that f of 2 is equal to 6. All we need to do is know what that integral is. So we go back to the graph. This time we're going to go from 2 to 6. So this area, what is it? It's just a triangle. Base is 4, height is 2, 4 times 2 is 8, times a half is 4. But remember, that part of the graph lies underneath the x-axis, so we're going to make that a negative 4. So now we know that that area is exactly, or signed area, I should say, is exactly negative 4. 6 plus negative 4 is 2. Okay, so that's f of 6. Let's do this one more time for f of 8. Notice we're going to do it a little bit differently, so just pay attention here. Here we go. F of 8 minus f of 6. Well, why am I doing that? Because 6 to 8 is the only other region that I have left to compute the area. So is equal to the integral from 6 to 8 of f prime of x dx. And so to find f of 8, I just put f of 6 on the other side. So finally, well, not finally, but you get f of 8 is equal to f of 6 plus the integral from 6 to 8 of f prime of x dx. This time we are using f of 6. And what is f of 6? Well, we just computed that. We figured that out to be 2. And so we just need to find what this area is again, just like last time. We go back to the graph of the derivative, find this area just between 6 and 8. Well, what is that going to be? Base is 2, height is 4. When you divide by 2, you'll get 4 times 2 divided by 2, which is 4. Since it's above the x-axis, we're just going to leave it as positive 4. So this integral is positive 4. F of 8 equals 2 plus 4. So f of 8 is equal to 6. And there you have it. We've computed values of the antiderivative when we were just given the graph of the derivative, f prime, and a single value of the antiderivative. And the way we connected those pieces of information was through the fundamental theorem of calculus right here. That's how we connected area under the derivative with the actual values of the antiderivative. All right. Now, just one more remark. Notice that in the very last part where I was computing f of 8, I used f of 8 minus f of 6 instead of f of 8 minus f of 2, which was how we did all the other ones. The point is, you only need to know one other value to get another one. Okay? So I chose f of 6 just for convenience because 6 and 8 was the only area we had left to compute. And we already knew f of 6, it was 2. So just to make things easier for ourselves, I used 8 and 6. Okay, but you could have also used 8 and 2, but you would have had to add negative 4 to that when you were computing the integral, because you'd be computing from the integral from 2 to 8 in that case.